Hi, my name is Brian Caffo, and this is the lecture on asymptotics in the statistical inference class. This class is co-taught with my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. I called this lecture a trip to asymptopia because asymptotics are this wonderful place in asymptopia. It's like, imagine a nice island with a sort of a coconut tree, right? And waves. Like, that's what asymptopia looks like. Great looking place. Looks like it's really fun. Type of place you might get some sort of rum drink with an umbrella in it. Okay, so sounds like you want to go there, so let's do it. So asymptotics. Asymptotics is the term for the behavior of statistics as the sample size or some other relevant quantity limits to infinity, or some other relevant number. So if something's limiting to infinity, maybe 1 over it's limiting to 0, so it depends on what's the natural thing to talk about. But usually it's n limiting to infinity. And by the way, asymptopia is my name for the land of asymptotics, where everything works out well and there's no messes. And I would say that the land of infinite data is nice that way. So asymptotics are incredibly useful for simple statistical inference and approximation. Nothing beats them. And then not covered in this class, asymptotic understanding of a procedure often leads to its understanding of its kind of fundamental principles, which is great, and that's why many statisticians study asymptotics to understand procedures at a very deep level. The problem with asymptotics is they generally give no assurances about finite sample performance. And the kinds of asymptotics that do give very good finite sample performance are just orders of magnitude harder to work with, and we won't even deal with them at all. Asymptotics form the basis for the frequency interpretation of probabilities. So when we talk about the long-run proportion of times an event occurs, estimating the proportion of heads that a coin will give by flipping it a lot and taking that proportion, that's really an asymptotic argument. So before we begin, let's just get a basic understanding of limits. And I think I can do this without too much mathematics. I think everyone would agree with the following process. If I took the number 0.9 and then took the next point in the sequence, 0.99, and the third number is 0.999, and the fourth number is 0.9999, and so on, I think everyone would agree that this sequence converges to 1, right? But so the definition for the limit is, here's 1, and this sequence goes up like that. So the definition for a limit is if we pick any distance around the limit, at some point the sequence gets closer to the limit than that distance and stays there forever on. That's what a numerical limit means. So for random variables, it's harder because they bounce around with randomness. So consider x bar the sample average of the first n of a collection of IID observations. So it could be the proportion of heads from n coin flips. Then we're going to say that, I have a little bit of a formatting error there, that x bar converges in probability to a limit if for any fixed distance the probability of xm being closer than that to the distance converges to 1. So if we have the limit, 1 in this case, and we have something that's converging to 1, but it converges like this, it's not that it stays in that distance in perpetuity. It's that the probability that it stays in that distance in perpetuity converges to 1, or the probability that it's outside of that distance in perpetuity is 0. So that's a kind of a probabilistic definition of a limit, which is hard, right? I mean, I think just even saying it, as I'm saying it out loud, it seems ridiculously hard. But it turns out that there's this super easy thing called the law of large numbers that says that if you have a bunch of random variables with mean mu and variance sigma squared being finite, then the sample average converges in probability to what it's estimating, the population mean mu. And so probabilists are going to would quibble about my definition of the law of large numbers, but there's a lot of variations, and they work very hard to get the minimal set of assumptions. So, I mean, if you're the kind of person that wants to learn it at that level, then you can go take a real class on advanced probability or something like that. But for our purposes, it just states that, you know, averages converge to what they're estimating, by and large. So law of large numbers in action. Let's do it. So I can't simulate infinitely many things. So why don't I simulate 10,000, because that's all I've got the patience to do. Okay, so my means, if I do cum sum like that, that's the cumulative sums of this random variable. So it's the first observation, then the first plus the second, then the first plus the second plus the third, and so on. And so then if I divide that by 1 to n, that creates the cumulative means. So here I'm going to plot the cumulative means, and then I'm going to put and it's because it's a standard normal, the population mean is 0, I'm going to put a line at 0. And what you can see is the cumulative means do converge to 0, right? They start out very noisy here, right? They start out very noisy, and then they converge to 0. Okay? And that's just the law of averages, law of large numbers. So it's nice that the sample mean converges to what it's estimating, the population mean. So why don't we define that as a property? An estimator is so-called consistent if it converges to what you want to estimate. So, you know, and I would say consistency is a very weak condition. It's neither necessary nor sufficient, but it's nice. You want consistency. It's a pleasant condition. But typically, most of the estimators we use are consistent. The good estimators tend to be consistent. You have to kind of come up with kind of pathological instances where you get a better estimator that's not consistent than a good estimator, but you can come up with them. And you know, this makes sense, right? If we go to the trouble of collecting an infinite amount of data, we want to get the right answer, right? Infinite amount of data takes a long time. So the law of large numbers basically says the sample mean is consistent. The sample variance is consistent. Sample standard deviation is consistent. Most of the standard estimators that we use we know are consistent. Also remember that the sample mean and the sample variance are finite sample unbiased. And the sample standard deviation is biased, by the way. Okay, so that is consistency, so things converge to what we want to. But there's this other interesting limit. So that's one of two of the most important limit theorems. The second one, the big one, the biggie, is the central limit theorem. You know you're a big theorem if you got central in your name, right? It's not the peripheral limit theorem. It's the central limit theorem, right? And so the central limit theorem, it's one of the most important theorems in statistics, maybe the most important theorem in statistics. I'll go out on that limb. So for our purposes, the central limit theorem states that basically averages of IID variables properly normalized look like standard normal random variables. And so the CLT applies in an endless variety of settings. So let's go through it. Imagine if we have an IID collection of random variables, mean, finite variance, and let's let x bar be their sample average. So remember, by the way, x bar has mean mu, its expected value is mu, and its standard deviation is sigma over square root n. Okay? So if we take this guy, which is root n times x bar minus mu over sigma, which is the mean of the estimate minus the population mean of the estimate divided by the standard error of estimate, that follows a z distribution for large n. So notice if we didn't have that square root n there, we would just have x bar minus mu over sigma. That would converge to 0 because of the law of large numbers. But it turns out multiplying it out front by the square root n is just the right thing that balances it and makes it turn into limit to a random variable rather than converging to 0. And then, usually replacing the standard error by its estimated value doesn't change the CLT. We still get a CLT. So here, let's go through some examples. There's some amazing examples of central limit theorem. So the way I got this example, this simulating a standard normal, is Francis Galton. He wanted to simulate a standard normal, but well before there were computers. So he did this, right? He rolled dice and used the fact that sample averages tend to look like a normal distribution. He used that fact to simulate standard normals. Really cool. So imagine we simulate a standard normal random variable by rolling n six-sided dice. Let's try and simulate what, like, say, Francis Galton could do. So let's let xi be the outcome for the ith die. Then notice that its expected value is 3.5. Its variance is 2.92. We already went over that. So the standard error is a square root 2.92 over n. That's 1.71 over square root n. So the standardized mean is x bar minus 3.5 over 1.71 divided by square root n. So if you go here, and the code for this is in the Slidify document, of course. Here's what happens if I just simulate over and over and over one die roll and then standardize it, and then I plot the density. Well, it's got 6 humps, right? So because it can only take on 6 values, and it's standardized in terms of the standard deviations from the mean. So it's not 1 to 6. It goes from -2 to +2, and then the back in the gray is the standard normal density. Okay. What if we just take 2 dice? We roll it twice, take the average, subtract off 3.15, divide by 1.71, divided by square root 2. Okay? We do that over and over and over again and get a histogram of what the distribution of the average, of the standardized average of 2 die rolls look like. Look how close to normal it gets after 2 die rolls. And then look at 6 dice. So roll 6 dice, take the average, subtract off 3.5, divided by 1.71, multiply the whole thing by square root 6. That gives you one random variable. Repeat that over and over and over again and get the density. And here it is. Look at that. It's almost exactly standard normal. So what I'm saying to you is if you had to simulate a standard normal, you could do it extremely well with 6 dice. Just roll 6 dice, take their average, subtract off 3.5 and divide by 1.71 multiplied by square root 6. Then you will have a random variable that is almost indistinguishably close from a standard normal. Now, I don't want to be misleading and suggest that the central limit theorem always operates so fast, but let's do a coin example. And I'll show you an instance where it doesn't work so fast. So let's let xi be the 0, 1 result of the ith flip of a possibly unfair coin. The sample proportion p hat is the average of coin flips. Remember that the expected value of a coin flip is p and the variance is p times 1 minus p. Therefore, the standard error is square root p times 1 minus p divided by n. So then approximately p hat minus p divided by square root p times 1 minus p divided by n, that guy is going to be approximately z distributed for large n. Okay. Ba-bam. There we've done it. Here is one observation. It has 2 humps because it can only take on 2 values, but the values are not 0 and 1 because we standardized it, so the values are -1 and +1. The standard normal is in the background. What if we had 10 coin flips? See, it's a little slower in this case. You still see the discreteness very clearly, right? And but it is looking quite normally distributed. And then 20 coin flips, looking pretty good. Looking like a standard normal would be a fairly good approximation to the distribution of the average of 20 coin flips. So the sample proportion comprised of 20 observations is pretty normal-ish. It turns out for the normal, it's going to converge faster. For the Bernoulli, it's going to converge faster to normality the closer p is to 0.5. So what happens if I make p, I forget what I made it in this case, 0.3, I think, because there's a much higher probability of it being low than high. Okay, you can see after 20 observations, it's still not close to a normal at all. Okay. So that's another example. And then we're giving, so obviously by making p smaller, you can make the convergence a lot slower, which is the problem with central limit theory. It never gives you a guarantee that you're actually converging. Here's an example of how we use the CLT in practice. So, we know, we know this guy, this standardized mean, the probability it's less than a z random variable is about that of a standard normal. Is about that of the associated probability from a standard normal. And so recall that if we have a standard normal, if we get 1.96 and negative 1.96, that about 2.5% of the standard normal lives there, about 2.5% lives there, and about 95% lives there. So that the probability that a standard normal, which this guy is approximated by a standard normal, the probability that lies between these two lines should be about 95%. Well, then if we tinker around with these equations in such a way that we keep track of things, we get the probability that this random interval contains mu is about 95%. So we call this random interval x bar plus or minus 1.96 sigma over square root n a confidence interval, because the probability that it contains the thing that we're estimating, if we were to repeatedly create these confidence intervals, is about 95%. Okay, so here's us reiterating that point. Therefore, according to the CLT, the probability that the random interval, that guy, contains mu is about 95%, where is about 1 minus alpha, where z 1 minus alpha over 2 is the 1 minus alpha over 2 quantile of the standard normal distribution. So it's not, that shouldn't be 95%, right? So if alpha is 5.05, then it would give 95%. But if alpha was 0.1, then it would give a 90% interval. So sorry about that. But we want the z, we want the positive, quantile, so that alpha over 2 lives in there, and alpha over 2 lives in there. So when we want a 95%, alpha is 5%, alpha over 2, 2.5% lives in the top, 2.5% lives in the bottom. Okay. So anyway, this is called a confidence interval for mu. Okay, a 1 minus alpha level confidence interval for mu. And we can replace the unknown sigma with the sample standard deviation s, and we still get a confidence interval. So let's just do this for an example data set. So here in Galton's data for height, we want the father-son data. X is our son's height, and we're going to take the mean of x. We're going to add and subtract the 1.96 standard normal quantile, standard deviation, divided by square root n. And then, because it's in inches, I divide it by 12 so that it gives it in feet. So 5.7 to 5.738 feet. Okay, so here's a useful thing that you can kind of take to the bank. For binomial, if you have an x is 0 or 1, then sigma squared is p times 1 minus p, and then the interval just takes on this form, p hat plus or minus z 1 minus alpha over 2 p times 1 minus p over n. If we were, and then because we don't, we're trying to estimate p, so we have to plug in p hat there and there. So that gives a confidence interval called the Wald confidence interval for p. It turns out not to be a very good confidence interval. But it turns out this function, p times 1 minus p, looks like that, and it's maximized at 0.5, right? So p times 1 minus p is and the max height is a quarter, right? Because p is 0.5, 1 minus p is 0.5. So so for p less than or equal to 0, 1, we can make this as big as possible by plugging in a quarter. So if alpha is 0.05, then z1 minus alpha is 1.96. That's around 2. So let's plug in 2 for our z quantile. P times 1 minus p is a quarter, right? So that's a quarter. Divide, square root 4 is 2, so that cancels with that, and we wind up with 1 over square root n. So here's my result. P hat plus or minus 1 over square root n is a really quick fire confidence interval for a proportion. So if you're somewhere without a computer and you got to come up with a quick confidence interval for a proportion, you're just adding and subtracting 1 over square root n. And if you can't do the square root in your head, just kind of do the closest square root, right? So if it's n is kind of close to 100, then you're just going to add and subtract 0.1. So if someone has a sample proportion of 0.7 and they have about 100 observations going into it, then you think, oh, okay, well, 0.6 to 0.8 is my confidence interval. Super fun, super easy trick. Okay. I don't know, it depends on how you define fun. Okay, so here's an example. You're a candidate running for election, and your advisor told you that in a sample of 100 voters, 56 intend to vote for you. Can you relax? Do you have this race in the bag? Can you just, go take your trip to Asymptopia, get your coconut drink, and lay back? No. Well, and you don't have access to a calculator. I don't know, because you've already gone to Asymptopia and you don't have a calculator. Okay, so anyway, 1 over square root 100 is 0.1. So a back of the envelope calculation gives you an interval of 0.46 to 0.66. Not enough for you to relax because that interval still contains 0.5, and you got to get bigger than 0.5 to to win the election. So not enough for you to relax. Better go do more campaigning. So anyway, some rough guidelines. 100, right? Square root 100 gives you 1 over square root 100 gives you 0.1, so you get about 1 decimal place accuracy. If you got 10,000 observations, it's going to give you about 2 decimal place accuracy in your sample proportion, and you need about 1 million observations for 3 decimal place accuracy. And here you can just, you can see what you get for however large n is, about what this interval gives you in terms of its width. Half width. It's its half width, right? Okay, so that's binomial intervals and kind of continuous data type intervals. Let's talk about a Poisson interval. So a nuclear pump failed 5 times out of 94.32 days, monitoring days, that it was observed. Give a 95% confidence interval for the failure rate per day. Well, if x is Poisson lambda t, then our lambda estimate is x over t, and the variance of that estimate is lambda divided by t. Just take the variance of that guy, take the variance of lambda hat, and you'll see that, right? Variance lambda hat is equal to variance x over t is equal to variance x divided by t squared is equal to lambda t divided by t squared, which is equal to lambda over t. Okay. Okay, so if we take our formula for generating normals, right? We have estimate minus its expected value divided by standard error, right? If we take lambda hat minus lambda divided by its standard error, square root lambda hat. If we do the manipulations, that works out to be that guy right there, x minus t lambda over square root x. That limits to a normal 1. So there's even better asymptotic intervals for this, but this is a quick interval you can do, and it conceptually fits into our framework. And you can actually get an exact confidence interval, not based on the central limit theorem in this case and in the binomial case. But the idea in the Poisson case is that it's very natural for t to go to infinity, not so your monitoring time goes to infinity, which is kind of the natural thing. And it turns out that does limit to a normal 0, 1. Okay, so let's just go through this example really quickly. So our x was 5, our t was 94.32, our lambda is x over t. Here's our confidence interval, right? And we get 0.07 to 0.99. And there's a Poisson test function in R which gives, I think, a better confidence interval, and that's that. And then in your regression class, you'll figure out another way to get the confidence. You'll figure out another way to get the confidence interval using Poisson GLMs, and I just give you the code right here. Okay, so that is the summary of our trip to Asymptopia. We used asymptotics to estimate probabilities from different kinds of random variables, and we used them to create asymptotic confidence intervals, which is just a simple example usage of asymptotics. So you should take a trip to Asymptopia. It's an incredibly nice place, and I hope you enjoy it there.